All right, let's enjoy example number 7 under mean value theorem and first derivative test. We have a function. We're going to determine increase, decrease, max, min, and we're going to graph it. And we do that, of course, from the first derivative test. So once again, the first derivative test requires finding the derivative and analyzing its behavior. We could do the product rule on this particular one, and that would certainly get us there. But I would be of the opinion that it would make sense to go ahead and distribute that x to the 2/5 power into the parentheses and create terms instead of a product here. And the algebra is conducive to that. So we have 9x to the 2/5 power minus, all right, what do? We add the powers, so 2 plus 2/5, well 2 is 10/5, so 10/5 plus 2/5 would be 12/5. That's easy to say, isn't it? All right, so that would be a rewrite of the original function. So now we'll take the derivative of that function. Terms, all right, power rule. So what do we have here? 18/5 x to the 2/5 minus 1, which would be negative 3/5. And then we have minus 12/5 x. Let's see, 12/5 minus 1 would be 12/5 minus 5/5, which is 7/5. Woo! Isn't that interesting? All right. I suppose one more little bit of rewrite that I would suggest doing, noticing the negative exponent here. So let's carry this over here. We're going to call this 18 over 5x to the 3/5. Goes underneath because it had a negative exponent. And then why don't we go ahead and put that x to the 7/5 upstairs because it had a positive power. And that would be a rewrite of our derivative in all of its glory. So, I'm going to transfer this over here in the interest of space for later on. So our derivative turns out to be 18 over 5x to the 3/5. Man, this is cool. This is really some restaurant quality algebra coming up here, isn't it? All right, so just kind of transfer this over in the interest of space. I wish I had more space. That's all right. We'll make it work. All right. So, first of all, I guess this time I might do things a little backwards. As far as the undefined derivative here, UND, undefined, all right? Well, yeah, you know what? Right there in that first fraction, 5x to the 3/5 power, division by 0. Wouldn't the value of x equal 0 cause that to be division by 0? That's an undefined, so we need to remember that. So our derivative is undefined at 0. All right. That was a quick little, I did mental arithmetic, 0 plugged in there would make that whole thing 0, wouldn't it? All right. And then as far as setting the derivative equal to 0, so remember we're doing our critical values. They're very important when it comes to the graph here. We will take this derivative, and I want to remind you that when you set a first derivative equal to 0, you're finding out where the tangent lines have a slope of 0, otherwise known as horizontal tangent lines, right? Those places where the peaks and valleys occur on a graph, we're going to have horizontal tangent lines. Peaks and valleys, max and min. All right, this is just algebra now. So to me it looks like we could clear both of these fractions here by introducing 5, that'll cancel the 5's in both of them, and x to the 3/5. It appears to me that if we introduce 5x to the 3/5 power on both sides here, that will clear all these fractions here. Remembering, 1, 2, 3, over 1. All right, so when we distribute that to both sides of this equation, on the first fraction it cancels the denominator completely and leaves 18. And then on the second one, what happens? The 5's cancel, and we're left with 12x to the 7/5 times x to the 3/5. And, well, let's see. Whoops. 12. 12 is still there. The 5's canceled. The 12 is here. All right, now, x to the 3/5 times x to the 7/5. Let's see. When in a situation like that, don't you add the powers? So 3/5 plus 7/5 is 10/5, and 10/5 is 2. So that became x squared there, didn't it? Wow, that just kind of cleaned up really nicely. And then 0 times that would still be 0. So, you know, upon doing a little bit of cleanup and so forth, that really had some very straightforward, very nice behavior, didn't it? So, I'll bring this equation up here now. 18 minus 12x squared equals 0. And notice we're lucky here because the x is in only one term, so I would advocate just algebra using inverse operations, whereby we would subtract the 18 over to the other side. Then we would divide by negative 12 on both sides. Might as well reduce the fraction. So x squared, let's see, that would be positive 3 halves, 1.5, if you want to call it that. And I'm going to call it that. Okay, 1.5 positive. And then x would be equal to, if you square root both sides, the square root of 1.5 plus or minus, wouldn't it? Okay, now, this is a situation where and remember, square roots create a plus and a minus. This is one of those situations where that's a messy number. It's a decimal, right? Messy decimal. And it looks like they are approximately plus or minus 1.22-ish, all right? So just for perspective when we go graph this, because who knows what the square root of 1.5 is off the top of my head. Okay, maybe you guys do, but I don't. So, you know, we're going to keep it in symbolic form, square root of 1.5, but let's just remember for perspective moving forward that that is about 1.22, all right? So just remember 1.22-ish would be those values of x, square root of 1.5. So, we had 3 critical values. We had these two, plus or minus, and we had, remember, the 0 from before. So, the square root of 1.5 plus or minus, about plus or minus 1.22, right? And I guess I could put our number line here. All right, so we have f prime of x above. And I'm going to leave it as negative the square root of 1.5, about negative 1.22, right? Don't tell anybody. And then 0, and then positive the square root of 1.5, which is about positive 1.22. All right, so the derivative, I wanted the f prime, the derivative was 0 at these two numbers, and it was undefined at this one. And we'll talk about why it's undefined at that particular value moving forward. There's 2 possibilities when you have an undefined derivative that are mentioned in the notes. So anyway, now we test numbers in each of these regions in the derivative, which that's going to be interesting here, all right? And I'm probably going to do some, like, hey, poke at the calculator, crunch it, okay? But, for example, negative 10 would be out here below negative 1.22, wouldn't it? And we're going to put negative 10 into that derivative right there. And it'd be imperative that you put that negative 10 in parentheses, and you follow the order of operations, and you're very careful with all of that. And I hate the fact that, you know, we're sitting here and I'd love to show you more steps, but I will just tell you, having done the question, that if you put that number into that derivative there and do the order of operations correctly, which is just algebra and arithmetic, you should get a positive number there. So the derivative is positive in that region. Therefore, those tangent lines have a positive slope. And as mentioned before, that means the function is increasing. So let's put that here. And we're going to put from negative infinity to negative the square root of 1.5. Let's keep exactness as much as we can. So, but that's about negative 1.22. Keep that in mind when we go graph this later on. All right. And then f prime of, what would be a number between these two? Keeping in mind that that's about negative 1.22. How about negative 1, right? Put negative 1 in the derivative. And again, you put negative 1 here, you put it here. Make sure you put it in parentheses when you crunch the numbers and all that kind of stuff. And I just have to keep the ball rolling. If you put that negative 1 in there, in that derivative, and crunch the numbers, algebra, arithmetic, it turns out to be negative, negatively sloped, all right? And therefore, again, that would be an interval from negative the square root of 1.5 to 0 where the function is decreasing. So in that beautiful decrease box that we gave you, we'll put negative the square root of 1.5 to 0. That's a decrease interval. That'll come into play when we graph the thing later on. Remember, this is going to become the x-axis on a graph here in a little bit. And then we have f prime of 1. That's between here. You put 1 here, you put 1 here, you crunch the numbers, all right? That's a mechanical stuff. I have to be a snob, okay? You're used to it by now. That comes out to be negative, all right? This is kind of like a cooking show, or I'm sorry, that actually comes out to be positive. Apologies. All right, let's fix that. That turns out to be a positive number. So from 0 to the square root of 1.5, this graph is increasing from 0 to the square root of 1.5, which remember is about 1.22, all right? And then, I was going to say, this is like a cooking show where they go, all right, mix these ingredients, and then they, come back and they're like, this is what the cake looks like now. So anyway, if you put a 10 in for x, go crunch them, hit pause. Go ahead and hit pause, crunch those numbers, see if you get the same thing I got, all right? And again, it doesn't matter what the exact number is, but when we stick 10 in there, that's negative, all right? So we have this pattern here that we'll use to our advantage. And again, from the square root of 1.5 to infinity, this thing is decreasing. All right, these are important things that help us get the general shape of the curve here. Up, down, up, down. So let's get after it. Let's continue here. So that's the increase-decrease aspect of this. The slide that says Roman numeral 2, ramen noodle 2, increase-decrease. And now we find maxes and mins. We already have the critical values. It's just a matter of determining whether these things actually create points. So this ordered pair here is negative the square root of 1.5, about negative 1.22. And this is where it gets interesting. I don't think I did this work ahead of time, I'm afraid. But wouldn't we want to go and put that negative square root of 1.5 into the function, right? And so this is where it's fun. You get to watch an old man see if he can get that in the graph, in the function correctly. Let me see if I can pull this off. So I'm going to put that number in up here in the function here. So, sorry, I'm sure this is like watching paint dry, but oh well. I got a number along the lines of 8.13. I hope that's correct. 8.1335, something like that. I'm going to stick with that, and if it's wrong, apologies. You can make fun of me. So, let's see. Oh, that's a max, isn't it? Increase coming in, decrease going out. So, let's list that as, and that 8.13 is an approximate. So if you want to put your ordered pair as approximately negative 1.22, approximately 8.13, that's totally fine with me. I went ahead and decimalized it this time. All right, when we put 0 into the function, you might go, wait, the derivative was undefined there. There's going to be an asymptote. Not so fast, my friends, because if you go put 0 in here for x in the function, you'll discover that actually comes out to be 0. There is an ordered pair there. Now, how could that be? Well, instead of being an asymptote there, as we're going to see on the graph when we're done here, that tangent line is vertical at that point. That's another way that a derivative could be undefined. There could either be an asymptote there where there's not a tangent line at all, or there could be a vertical tangent line. And then 0, 0, let's see, decrease coming in, increase going out. Wouldn't that be a minimum? So let's put that there. And then positive the square root of 1.5, which I'm going to put as a decimal when I list it as a point. I'll lose a little bit of accuracy, but that's life. I'm okay with that. So that would be, again, we're putting it in the function. right? So I think it's the same as the other one, but I'm going to confirm that. So I'm sorry. Oh, shoot. This is exciting, isn't it? Oh well, go have a cup of coffee or something and see if you get there. Let's race each other, I don't know. But anyway, put the square root of 1.5 in there for x in that function there. I guess I've got stage fright here. I know I'm nervous in front of large audiences here. Let's see, and then, yes, 8.13. And that's coincidence, they don't have to be, but it seems to confirm. So, let's see, what's that point? Come in, increase in, decrease out. How about a max, right? So, the decimal equivalent, approximate equivalent to that, 1.22. I'm listing those in decimal form because, you know, are we going to put the square root of 1.5 on our x-axis when we graph it? Probably not. All right, so speaking of graphing it, why don't you catch up with that, crunch some numbers if you want. Let's come over here and get a quick graph going here. You guys have a whole big old swatch of graph paper here. I hope this is working where you guys download the PowerPoints and all that, and I hope you're able to somehow print off the homework. And I'm fine with you sending me pictures of them. I don't know how you would do this, multiple choice, for example, you know. So, which of the following graphs go, that's not math, okay? So anyway, this is how I've decided to do this. All right, so I think we're good. I think that probably the x-axis, I'm going to go in increments of 1/4, and I determined that by looking at these values of x. That's about 1 1/4, negative 1 1/4. So anyway, 0 here, 1, 2, 3, 4, that would be 1, that would be 1 1/4. This would be 1, 2, 3, 4, negative 1. I'm going in increments of 1/4, right? So negative 1 1/4. That's about negative 1 1/4. Just use these points to determine your scale. The y values are 8-ish and 0. Okay, I'll scale the y by 1s. Therefore, 1, 2, 3, 4, 5, 6, 7, 8. I'll just kind of put 8 there as a landmark. Let's start plotting these points. We've got negative 1.22-ish, 8.13. Negative 1.22-ish, 8.1. Just get me in the ballpark. All right. Then we've got 0, 0. I'm looking at these ordered pairs. And then we've got 1.22-ish and a little bit above 8, just like the other one. And then we've got the increase, decrease, increase, decrease. And I'll put tangent lines on here as we do this. So from left to right, increase, hit that point, horizontal tangent line, right? Derivative is 0 at that point. Then it decreases to the origin. But here's the interesting thing about that. When it hits that origin, here's the deal. That derivative is undefined there because at that moment, just at that one point, that tangent line is vertical. Now, you guys don't have to put these tangent lines on your graphs. I'm just trying to illustrate the relationship here. So that ordered pair had a vertical tangent line. Then it increases to this point. And then, again, has a horizontal tangent line at that point, and then it decreases forever beyond that. So there you go. There would be your beautiful graph of that. Once again, you don't need these tangent lines on there. And so I thought that was kind of an interesting graph. And, you know, I guess the shape just kind of seemed sort of interesting to me, and I was trying to think of what that conjured up to me because I'm looking at that graph and I'm going, that graph, I'm loving it. Yeah, so, you know, guys, I've told you guys that I have a math agent, just like professional athletes, professional mathletes, you know, we have agents. And, but my agent, kind of on this one's not on the ball because I don't have an endorsement contract yet with McDonald's. So I would love to someday be able to say that this commercial, this this example was brought to you by McDonald's and then, you know, reap the financial rewards. That hasn't happened yet. So if anybody out there knows anybody with McDonald's, call me.